Nós vamos cozinhar aqui dentro. Yeah. Obrigado.
Jose, remember this issue in Janelle.
I know that. You just tell me when to stop, Daniel. That's your job. Not an hour, but 10 minutes late, so it's 50 minutes. And then we have a problem. There appears to be on the battery.
Ah, okay.
Tem uma bateria aqui, alguém deixou ligado e foi sim. E eu não fui o último a falar, hein? Eu posso. Okay, we are live again. Okay. Do you know, Daniel, these kids are a bunch of amateurs. These are the only professionals. I've been doing conference in my life. The ruling conference is 3 hours of sleep. You can go to bed anytime you want, but you have to be there 8 in the morning. See? Kids these days are getting too soft. They just can't handle it more. If a guy that's 50 can do it. Okay, that's the real effect. Right, but you have to handle it. What's the story? You have a lot of time to sleep after you die. So. Okay. Let's tell you a few stories today. Since Daniel told me I have 50 minutes according to the clock. Have a seat, Gene. 50 minutes according to the clock. We are going to go over it. So, remember what I said yesterday, and I will repeat one more time because they're going to be hearing these stories for a long time, and you probably heard. We talk about funnel landscape, we talk about minimal frustration. So, which are these structure-based models or GO models? These are models that are built artificially in such a way that by construction, you remove the entire energetic frustration. You get the native structure of the protein, and you say, I don't care if they're dihedral angles or tertiary contacts, I make them attractive. And everything that's non-native, I make them repulsive. So the interesting question, basically, you're not predicting a structure of a protein. You cannot be predicting a structure of a protein if you use the structure to make the potential. Right? But the idea is, when I write the potential of this form, can I demonstrate what I told you before, that basically, proteins have energetic frustration and topological frustration, but the energetic frustration is sufficiently small that most of the interesting heterogeneity, which intermediates appear, which transition state to observe, which contacts form first, they're determined by geometry. So these models allow us to check that, because we construct this model and then we compare against experiments and we do that. Okay, like I said, this one is the simplest one, where we fully coarse grain the protein and just represent each residue by a bead. When we call a C-alpha model, doesn't mean that you only have the C-alpha atom, it means that you only have a bead in the position of the C-alpha atom, which is about a little bit of the size of the amino acid, and you go from there. Okay? But I decided to add a little bit more to it today just for fun, because people had a discussion yesterday. And remember when we discussed CI2 and SH3, and we discussed that basically the fact that some contacts are formed early on has to do with the geometry of folding, has nothing to do with the energetics. It cannot be energetic difficulty. So that's a non-funnel-like character. But I want to show one model that Mark has shown, that was the group work together with Angel. That's the model for sulfation. Yesterday you had this discussion by Gerson, and people have the situation that's the following. And I have a simple problem for you. And that's a beautiful problem that you actually can do. You can, for example, get an entire box of water, use your favorite water motor, SP3, SP4, whatever water motor you have. Put it into a box of water and run a big simulation. Right, so I have here a bunch of water molecules and a lot of computer time to waste. Okay, and I run a big simulation. And then I get, for example, if I have two methanes there, they're these are sort of big hydrophobic blocks of 4 angstrom diameter. I say, what's the probability of opening cavities inside of this water? The water fluctuates and suddenly you open a cavity. Remember I told you, a cavity is very, very expensive. The larger the cavity, the more problem is. So when you do that, and you ask the probability of opening 2 cavities just because that's what you need if you're talking about 2 balls, and the cavities have to be the size of the ball, but you're just running water. You can get part of the BMF of attracting these 2 waters as being minus the log of the probability of opening these cavities. So when you plot here, minus the log of this probability with a few RTs and KTs in front of it to make sure you get the right units, right? There's an RT in front of it that's got a free energy light. You can actually put here, and you plot that versus the separation between these cavities. That's just a water simulation. So I have these very unlikely events. What I get is something like that. Okay? You go to something that basically, and you see that becomes, you have a maximum, and you have something that say basically sinks this water right, rather than collapse on the top of each other, right? That's the best solution, that they start to come apart. So what happens here, why do you have the second minimum here? Because you can say these things are very happy to be overlapping. As more overlap they are, the happier they are, because they're opening a smaller cavity, right? But then they just come on separate themselves when they're just in contact. As soon as they start to move away from each other, they open a space between them. And if you can't fit a water molecule in that space, you create what? An additional void. That means you become more entropically alike, because now you need even more space of fluctuation. That's what gives you this maximum. And then suddenly you go apart a little bit more, and you get to squeeze a water in between. Then you have the second minimum. Okay? Now, this is just the potential of the water. Now I'm putting my methane in there, so I have to dress this thing here. I didn't do it well enough. I have to dress this thing here with repulsive potential that comes from the hard sphere. And when you put all this together, just exclude volume of the hard sphere of methane together with the probability of water, I got a potential like the one we have here, like the one I have on the board. That looks like that. Okay, and that's exactly separated by a water molecule. That's the typical interaction between 2 hydrophobic groups in solution. Right, so voids are very expensive. So even though they're hydrophobic groups, there's a maximum here, and there's another one. But there's an interesting one thing here that happens here. And it's not on this slide, but I'll tell you. Now you apply pressure into the system. Now the water is very sensitive to pressure. That's what we discussed yesterday. So when you get those high pressures of 1 kilobar, like was telling yesterday, the basic pressures, 5,000, 10,000, that's when they start the nature. When you happen these things, you distort the water structure in such a way that this entire curve that I show you, the initial curve here, sort of moves this way a little bit. You sort of squeeze the water in there. Right? So the probability of water, the water starts to pack so much better, the things move in. What happens when these things move in? You're fighting with the repulsive potential, right? So what happens? This minimum goes up. And the pressure saturation happens when this minimum go up and up, that this one wins. So it's very counterintuitive, like I was discussing yesterday. But it's counterintuitive because if you don't take the water into account, you don't get it. Right? So you have to squeeze and repack the water. And that affects the way the protein does. The beauty of this thing for you guys is basically, force fields are not good enough to give you thermal denaturation. The force fields, even with this model, if I compute the simple problem that's 2 methanes into water, you're going to find the pressure that this minimum starts doing is exactly the pressure this protein starts to nature. What tells you that the pressure denaturation is a very local effect. It's not something you have to put many water molecules and plenty. That's why the local force fields can handle, right? Because you don't have to put higher order correlation. So even though you have this sort of very simplified force fields, in a sense, the way that you don't have long distance correlation, that's enough for pressure denaturation, because the packing of the water around the cytophobic group is what's important, right? While temperature denaturation is much more complicated. You can, the current force fields cannot get even close, right? You know the secret that is you run a concurrent force field, no water freeze, actually becomes very less around 200 Kelvin. That's right. So that's what happens if you run the current force fields, because they have been sort of calibrated to behave well around room temperature. But then you go out of that range, situation becomes problematic. Basically, you have to start to cheat. You can cheat. You always can cheat to give the right temperature dependence, but the current force field alone cannot do what pressure denaturation can do. So the interesting thing about the folding of SH3, by the time that now I have a GO model, but in addition to my attractive interactions, I say that instead of having just the current, the 10-12, I put a potential width to minimum that allows you 2 positions. One that's what we call the dry contact, and the other one is the water separate contact. So when you run the simulation, the first step in the simulation here is just like what we discussed yesterday. I'm just going to show back here. That's the part that is first to form the local structure, then you get these things here, then you bring like this distal loop, the distal loop and the distal hairpin and the diversion turn, you bring them together, you pack them and you make the core. That's what you're doing here, right? You bring these parts and you make the core. But the difference, if I just go one slide further, is that here it's just like the protein folds, but with the fact that you still have some waters into the core. So the first stage of folding, the protein is very close to the folded protein. If you look at the RMSD, they may be a couple angstrom apart. It's very close, but all you have is a hydrated core. And then the next step is basically you can squeeze the water out. And now you can argue about, first of all, there's several things that you are, as a physicist, you can think about. If you talk to chemists, they love to use the word rate determined step. What's the rate determined step? Like, I don't care about anything else. If you understand the rate determined step, understand the reaction. So what's the fast event? Is the event where you get the correct geometrical shape, or is the event where you expel the water? You did both. And here I draw 2 times out of this particular simulation. But I'm sure if you let me fool around, and even experimentally, I can make this one shorter and this one longer, depending on conditions, and still you need both. Right? To make a situation that the outside is very unfriendly to water, I put some other things, and it's going to be hard to expel water. And I can put a situation where I completely remove the barrier. Right? I can make this one shorter. But the bottom line is a double effect. You fold into a protein, it just looks like the initial protein is water on the core. The other interesting thing, I'll just comment, and I'll let you guys think about it. What's the folded state? A lot of function may happen here, particularly in SH3. SH3 has to open so that the ligand can bind. So the fact the core opens a little bit and close makes a lot of functional sense. Right? So the thing will have a rock core solid, like people say, you have such a hydrophobic collapse that the hydrophobic core gets glued so bad nothing happens, then this protein will never have function. Right? So it makes a lot of sense. So even so, this state is the ground state. This state is actually the one. There's another thing I'll tell you. Also, enthalpically, this state is better Water ZC can give you a little bit of extra entropy, the protein, so you have competing effects. Okay? So that's just for you to get a feeling that basically when you talk about pressure and water, you really have to consider the salt and the protein as one thing. If you just think about the one alone, then you get the counterintuitive feeling that you have. How damn I squeeze something and expand? Right? But that's where you need the two things together. So, that's just for fun. That's just for fun, and it's an interesting thing. This is an all-atom simulation of SH3. This is a free energy in 2 dimensions, just to have a little more resolution. So you're going to look at a plot, and I'm going to help you with this plot a little bit. This is an old simulation in 2002. These are the first ones using all atoms, everything. We can do much better now. Computers are much faster. So this one is, like I like to say, that's the sort of childish simulation, right? Compared to today's standard. But it's enough to bring up the kind of situation we have. So here we have a free energy profile. Here's the radius of gyration versus Q. Linear simulation, you can put RMSD versus Q, right? Just to plot in 2 dimensions. So if you look at these things here, this appears to be a full downhill folding. So just look, you go from high potential to low potential, right? You come up here around, these things are kilocalories per mole, about 10, or you can say KT, give or take, it's fine from here. There's a 0.7 factor here. But you come from, and you just come down. We know we have a barrier. First of all, I can tell this protein at these conditions have a barrier of about 4 kTs here. So basically, you know the simulation is not getting the barrier of the transition correctly, right? So if I plot this one, what I mean by that is, if I plot this problem, you should get something like that, right? Like I have shown you. And you're actually getting something where the barrier is gone. Right? I mean, it pulls up here. Right? The question, the barrier is gone. And so this barrier is disappearing. So let's think about it for a little bit. But there are interesting things first of all. Before being negative, let's be positive. When I run the simulations, and I start to run into situation, actually this is not a full folding simulation. You have to ask, how do you get this thing? I told you yesterday we were unable to run full atom kinetics. So what people did, they ran several unfolding runs. Then they beam around the unfolding runs, and got around this grid of beam states. You run different simulations there, and then you try to patch all the histograms. That's a standard trick, and there's a lot of numerical troubles that can come with that. But that's how it's done. But there's a main problem here. On my initial runs, there was no folding run. They're all unfolding runs, so keep that in mind. Okay, and I assume that's good enough, okay? I did that. So now, when I look at the results on this landscape, what I observe is actually kind of nice. Let me just put everything here. Oops, see, too fast. Okay, when you run the simulations here, become kind of nice, because you have a log. You see, you start on what you expect to have the unfolding protein. I'm just plotting here. See, there's no structure, but it's collapsed, right? So I don't think that's a surprise for you, but basically it's not an unfolding protein, it's not a long stretch things, right? Things that are, they're entropically very unlikely to happen. So what will happen is that the area where you should have a transition state should stay on this potential. So at least let's look geometrically where the transition state should be, even some downhill. You see first, before it, what you have. You start to form local herpes, as the goal model was giving me, so it means that basically means that even this force field is able to give the right aspect. When you come to the transition state, you have to bring the divergent term, that distal herpes and divergent term together, so that's fine. Then you jump around this region here, that has these two things here. That's exactly the full protein, but with a hydrate core. And that's this minimum here. And then you squeeze the water. So the all-atom simulation, qualitatively, we are getting agreement. What tells me even this force field, on those days old, was able to give what the goal model gives. I mean, it makes sense. It's really a funnel landscape. Even this potential is sufficiently funnel-like, right? They agree what you observe over there. Now, why do you have the wrong slope? You can say the force fields are not good enough. Okay? It's still amazing that anything works. Right now, we're trying to calibrate. If you remember, water potentials are calibrated to give water properties. Protein potentials were calibrated to give most of the protein around folded structures. No one was given to say how water reacts with hydrophobic, that's not as being calibrated. So it's amazing these things even work. Okay? But it means the folding is robust enough that does. But should I just blame the force field? No, that's too easy. The other thing is, there's a good chance that since I only look unfolding runs, I haven't done enough sampling on my unfolded basin. I run some unfolding runs, I sample some states, but there's a great chance of undersampling. Unless I can observe multiple transitions back and forth between these two things, and now we have been doing that with rapid exchange, I cannot guarantee they have the proper balance between the equilibrium between these two things. And if I start to make these things more repulsive because I don't sample enough, means I have less entropy, you see it's kind of pulling these things up and I can start to remove the barrier. Undersampling may be one reason why the barrier is not there. So one thing you may blame the force field, it's very hard. But remember, undersampling is something to always think about it, right? That's something that could be fully responsible here. I'm not trying to say. But the amazing thing is, energetics is very hard to do. But geometrical properties are very robust. That's why these simplified dome models can tell. But tell you, these proteins are sufficiently minimally frustrated that even if you don't do the energetic totally right, you get the geometrical aspects of folding quite well. Right? Even here, like I said, if I know what transition state is and I play there, I get the right structure as I observed before. Okay? Now to conclude this story here, since I'm showing a lot of stories, this is sort of a fun thing, basically. This is an interesting thing that basically, the way people do it, and just so that you get used to 5 values, the way people do is most of the 5 values, they remove residues, do a mutation and see how they affect folding. You know what I told you about that. Most of that exercise is done by what people say an alanine scan. You just remove everything and put an alanine on the place. You don't want to put big things because then you have problems with packing. But this one's an interesting one, SA3. Luis Serrano is a good experimentalist on this area. He's actually doing a lot of interest in system biology now, more than folding experiments. He's a sort of good guy in bioinformatics and laboratories. A very nice guy. Used to be in Heidelberg for a long time of his life. A very funny guy. Lived there for almost 12 years. Good Spaniard. Didn't speak a word of German. And I say, Luis, you live in Germany for 12 years. Why don't you speak any German? I say, it's already hard enough to have to live with them. Imagine you have to understand them. So, that's just joke. I have 2 Germans in my group. I love to tell that story. And he used to tell that his group was half German. He was always complaining about it. He was a funny guy. He's a Spaniard, what do you expect? So anyway, I have 2 grandparents that came from Spain. I know the package. I have a little bit of it. Okay, I was on Mount Michigan on my mother's side. I have the Martinez and the De La Rosas. They're just not on my name, but they're there. Okay, so the fun thing here is he decided to do a better mutation. You look at all these amino acids in the core. And these amino acids, if you look about the base, they are threonines. They are valines. Okay? So he looks for these valine amino acids. And why that's nice? Normally, like I said, you look at these valines and he has like I think 6 or 7 there. 1, 2, 3, 4, 5, 6. Here, I think there's one more, but they are all right on the core. And he can mutate now. Instead of doing alanine scan. If you do an alanine scan, here's the valine, here's the just the amino acid. So here's the side chain. What you're doing is you're removing it and you're forming an alanine. But it's just like taking part out of it. If you start doing this mutation, you do valine by threonine. It's like removing a CH3 group and replaced by an oxygen. The beauty of it, the nice thing about these amino acids, because although you're changing a non-polar group by a polar group, the packing is the same. The alanine, you have the leftover packing, so you can wonder how the things are. So this is a great mutation in a sense that basically is really you expect that you're making a repulsive, energetically unhappy situation, but you have no problem with packing, because exactly the same packing, oxygen should be as big as the CH3 group. So that's a nice mutation. And that's true. What you observed is that all these mutations destabilize SH3 exactly by the same amount. About 1.5 kilocalories for every number, something like that. But it was great, because now you have 7 mutations that, when you remember, destabilize. If you think about the situation about 5 values, what's important in transition state, right? Just refresh your memory. The thing on the bottom is how much you destabilize. That's how much you change the stability versus how much you change the barrier. And that's to say how much the residue is structured in transition state or not, and how much is important at that point, right? So here I have a great system because this number is exactly the same, the perturbation is exactly the same, you don't feel like you have to rely on the ratio. So Luis was actually doing the experiments and say, why we're doing the experiments, you don't try to figure out which of these mutations, even though they spell out the same amount, will affect the folding rate by a lot or will not affect the folding rate by a lot. And Margaret started to work on that, and then we published this paper together, and the fact we published the paper together is already a good indication that something worked out, otherwise I would be hiding this information. Okay? But that's a sort of a nice story. And why this worked? Because it sort of come to close this entire package that I present to you in this idea. Why the Go model work? Because minimum frustrate, I agree with the atom, and why can you use that for experiments? So what he did, I'm going to show the results here because you guys can actually do better than we did. These are the results of the simulations. And when you notice that V54, value 54 and 53, when they're mutate, they substantially affect the rate. The other ones affect almost nothing. Nothing that you can imagine. These arrows means these things were much slower than the overall time that we simulate. This one it was on this range, but this one we never converged. There are too many runs. Their simulation time was not long enough. That means you're not able to fold on that. And when you do simulations like that, the way you plot it to say that you did bad simulations is to say, I have several runs that were not successful. That tells me that I include the total time of simulation, but I know the real answer is longer than that. That's what the arrow is telling me. It's telling me that. The other thing is, even here, they still a little bit faster than the case. If you plot correlations, the potential, all atoms get even slower. But still, you can get the trend from here. So the answer was 54 makes life very unhappy. 53 is slowed down substantially. And the other ones should affect little. And that's exactly what you observed. The fun part is, if we believe the system is minimally frustrated, then we could say that these things are dominated by native context and therefore geometry is important. I probably could have said that without doing the simulations. And that's what's telling you. If you look at the results now before I show you, see, here's where we start the simulation, right? You have this local structure. If you have a look here, that's what a 44 is. 44 is vital to stabilize this herping. You mutate 44, this herping gets very unstructured on the unfolded base. You get more structure here, and you have a very hard time getting to the stage where you have to bring these two parts together. Right? It's the worst possible part of the protein. But you probably, if you had paid attention to this picture, you could have guessed without doing that. 53 is on the herping, but it's on the outside of the herping. It's not actually stabilizing the hydrophobic core of the herping. But it's very important for the distal turn, this distal herping to come to diverging turn. Remember that long-range contact. Means that when you make that less stable, that contact becomes more unlikely to be formed. So the barrier for folding gets higher. It can get formed, but become a very unlikely event, and we slow down the rate by a lot of amount. We still go by the same route. If you look at the other ones, 58 here, it's really just the tail of the herping. So the question, if you have a nice, well-formed herping and one that's just with the leg shaking, doesn't make too much difference for folding. Okay? If you look V9, it's really at the end, it's the last part that folds. You have the herping unstable, but it's not a big deal for folding. 23 is out of the action. So it's kind of nice, because now you have a story where you have a theory, you have an analytical thing, you comment about the ideas, energetic frustration is small, therefore you're going to observe the geometric effects, you can see a lot about the ground state, then you run an all-atom simulation that agrees with that, and you're able to do the experiments. sort of a nice story that tells you about, there's several years involved in this research because something was done in a couple of months, but tells you one thing about when you deal with these problems. There's not like one technique or one way to look at the problem. You look multiple approaches to try to see if they're consistent. And also, you have to look on the totality of the experimental facts. One of the big traps, particular theoreticians fall on it. They believe that analyzing experiment is like going to a restaurant and choose just the plates you like, and the ones you don't like, you don't choose. Okay? So if you get a complex system, you're always going to find some experiment that agrees with your data. Right? But that's not allowed. You have to be able to explain the totality. That's a good exercise in a sense, and that's why predictions become very important. Because this sort of blind experience is not because blind is necessarily better. Blind, and it's not because you are dishonest, but it's a way that even unconsciously you cannot cheat. Right? So it's a way that basically you just don't know that information. And sometimes it's good that you don't know that information in a sense that you go out and you say something. And just for you, sometimes you don't agree, and don't agree is also good. Tells you there's some problem with the current working model you have, and that's how things evolve. Okay. On the last 20 minutes, let me tell you a couple of fun stories here. I won't go to the end, but I think Cecilia will tell you all the hot stuff in protein fold. So, but I'll tell you a couple of stories for you anyway. So the idea is, can you extend these ideas where I talk to small proteins? It's just about small proteins to large systems. And now, I apologize, but I'm just going to fly over. That's my last half an hour to show you a few examples. I think I gave enough details that you can do these things. So actually, the first interesting, basically, can you go to larger systems? And can you talk about function? So let me tell a couple of stories. The first story was actually many years ago and was done by Cecilia. It was on QI. That's a larger protein. That's also a Mr. protein. But the interesting thing, there are many proteins that when you fold, you start from fold, you go through intermediate, and then you fold. But QI is interesting because you cannot get that from here, you have more sampling. There's one intermediate that's a trap. It means you form, and you have to break before you go, and then there's a real intermediate. The question is, how do I have a trap? And that's the first time that basically you're able to predict the experimental trap using a model that has no energetic frustration. I'm using a Go model. If I can predict the trap, I know it cannot be an energetic trap because the model by construction doesn't have it. And the reason for that is actually very cool. It tells you interesting things about how the factor geometry can really affect the mechanism how things do. Is if you look at protein QI here, it's down here. This protein has basically 5 alpha helix with a core of base strands in there. And this is the top part is equal to the bottom part here. We don't use to draw half. This one's just symmetric, so don't worry about it. But what tells you, this is the nature of this trap I show you. Where the trap tells you this protein form, these are the alpha helix, right? The alpha helix are close diagonal, they're formed early. So the first things protein form are 5 alpha helix, but with a disordered core. The contacts of the core are disordered. But actually to fold, you have to break these 2 helix, reorganize the core, and that's the real transition state for the process. So that's why you have the trap, because you form this helix too early, and you cannot do that. So you have to go over this additional stage of breaking them. What's very nice is if you look at the paper of Luis initially, and you read carefully, he says, if I look the folded protein and the trap, and I run CD, I have the same content of alpha helix. And that was something that was very curious for him. How do you have the same content of a fully folded alpha helix? Because your trap is actually has all the alpha helix. You just have disordered alpha helix instead of fully packed alpha helix. So you get something that actually come up on the context. Okay? On the interest of time, I'm going to skip interleukin-1 beta. It's another protein that Cecilia worked on. I want to go on a couple more topics. I just want to show you a couple of different things. Now, there's an interesting thing that comes from a funnel landscape. One of the main things that come, people say, what's a consequence that if you have a nice funnel? If you have a nice and smooth funnel, where your energy is proportional to Q. The energy is proportional to the contacts. So you're going to have something that looks like that. Okay? As you stabilize the protein, you also reduce this barrier. Right? That's what people for a long time, if you have been, is what people used to call linear free energy relationships. Okay? Actually, the position of the transition state changes very little. I'm going to call that Q star. There's lots of work these days saying how the position transition states change. If the position transition state change, then you expect that basically some new states are appearing there. But the barrier goes down. That's something that's a natural consequence of running a linear free energy relationship. And if you do by perturbation theory, that's how you can get phi values and things like that. This was an interesting protein that people were studying. And they claim on the old days, and that's good for function, was here is a protein that completely destroyed this idea that on landscape theory. And the reason for that, so this is, if I can tell this story, it's fine, I have enough time for this story. I won't tell just two short stories. One is this protein is what you call a coil-coil protein, right? So you have like two, is a dimer, is a homodimer, right? And each unit has a helix and a term. Right? This is exactly coil-coil, and you have this 4-helix bundle, sort of defined structure. Okay? That's the way this protein does. They came to the core of the interaction where this helix, this is a single monomer, just right? And they decide to play with this monomer, and they decide to play with this monomer by stabilizing it. So if you look, there's this pair of amino acids interface. And they said, if I do a perfect packing into this pair, by mutating more and more the core, that's what I mean, this is the wild type, and you see now you have more and more mutations, where you replace the packing by pairs of alanine and leucine. Right? And then you switch the alanine, leucine, leucine, alanine, alanine, leucine. So you start to get something where you believe you're going to stabilize this entire hydrophobic core with a large group and a small group and fully organized. That was the idea by Lynn Reagan and people over there. Now, what's cute about this protein is, when they did that, the idea is to stabilize this protein. The first thing is, look, this delta G0. That's the stability they get by mutation. This is the wild type, and then they go all the way to all the 8 mutations. You see that pretty much they change by very little, and they jump all over the place. These things may vary by a couple of kilocalories per mole here or there, but it's not like they really fully stabilize the protein. Actually, the first one was minus 7.7, the other one was minus 7.5. So there's some repacking, some reorganization. You're not buying yourself too much of the stability. However, they observed one thing experimentally. This is what we call relative rates. If I call the folding rate 1 and 1, just because it's relative, or whatever the scale is. So imagine on K folding wild type and K unfolding wild type. Look at that. The folding rate increases substantially. And the folding rate increases even faster. Okay? So here is a situation where you're telling me that what's happening here is these two basins are exactly the same. They're changing very little, but the barrier is getting substantially smaller. That's something that's very known when energy landscape like. The question is, you have to have something else going on. So in a sense, the conventional idea, you have a funnel landscape, and you can't explain the situation. Okay? So this is slides were done by Code 11. You love to put these Sherlock Holmes here, see how can you solve that mystery. Okay? But that's an interesting case. So, now, if you come from physics here, since you're talking about physics school, there's one thing you learn if you have done with physics, particularly condensed matter, soft or hard doesn't make any difference, is the fact that basically, if you start to symmetrize too much things, systems may tend to break the symmetry on their kinetics. Right? So you have to remember. So the real question is the following thing. Here's the wild type protein, And if I look at this wild-type protein, it forms what they call this anti-configuration. That means you have this helix here and this helix there, and if you look to the top, they just fold like that. But the question is, you can call anti-parallel, whatever if you want. The question is, why don't they fold like that? Now, you know that for functional reasons, you have to be anti. Now, what they told us, looking in vitro, when they looked at information in vitro, is to say, no. But this protein is still active in vitro. That means it still binds RNA in vitro all the time. Therefore, it has to have this configuration. So you cannot say anything else is taking place, because I know in vitro this protein always binds RNA. The trouble was, they never told how strong bound RNA, but they said it bound RNA. But then the new experiments started to come up. And they started to bring possibilities for this situation. And what the experiment told you is a couple things that I want to present to you. What the experiments told you is that basically, first of all, although several of the samples work in vitro, they didn't work in vivo. They work in vitro here, but the animal died when you did this mutation on the animal. Minor mutation around the wild type, just a single mutation you do, but when you try to do multiple mutations, the animal dies. So basically, although binds RNA in vitro is deadly, so you expect something else is taking place. And then, there is the fact, they did some mutation, what they call this alanine isoleucine mutation on the core, and this one the crystal structure gave a real nice parallel structure, now what you call syn, but that doesn't bind RNA. But that's a hint that this structure can exist. Right, so you already have this situation. And they even find this, when you do minor mutation, is bisecting things when these things go across like that. But that's the situation now, can you have multiple structures? So when Kolbe came around, the first set of experiments that he did was to say, let's assume, let's do a funnel to fold one structure, and let's do a funnel to fold the other structure. And let's see if this protein is actually two funnels. That's the possibility of having two competing funnels. And what he noticed from that is the following thing. Wait a second. Yes. What he noticed for that is that basically the folding towards the syn structure is much faster, I'm just nothing, is much faster than the folding towards the anti structure. So Kolbe noticed that, and actually did a little more work on that reason. So instead of just doing two things, we create what we call a dual basin, or dual bow, or dual structure, where now I do a model, okay? I get this protein, and if you look, the contacts are very similar. I say the contacts of the two helix are attractive, but you make the contacts for the syn and the contacts for the anti-attractive. So you let both compete. If you make all these contacts, and you can justify that because you can show the contacts, amino acid by name, they are all the same. So it makes a lot of sense. You just change the geometry, but just the local contacts, the same pair. But now you just allow the two geometries. And if you do a simulation where you allow both contacts to be exactly the same in energy, right? Remember my goal model, my epsilon, the interaction is all the same. So I keep the model entirely energetically symmetric, then I know just the difference between geometry that you guys can compete. And when you do this model and you run the simulation, what you observe is, here's the anti-parallel, here's the parallel, and you observe the parallel has a smaller barrier. The one that's like that. And that's expected, because this is like my 5 values. The dark colors means what's the structure of the protein in transition state. Dark colors mean this one has a transition state that's more structure around the end and no structure here. And the one that comes anti-parallel has a more distributed transition state. So this one is much easier to fold. Why? Because this one you have a much smaller nucleus. The geometry just helps you. By the time you make the nucleus, then you just bring all the legs down and you're done. Not here. So these ones entropically, the barrier, although energetic, is the same. It's much more disordered transition. You have to pay a less entropy price to fold, and that makes a faster folder. So what that tells you? That tells you the following thing. That tells you that, first of all, you can move between these two minimas. You can just go back and forth. Now, nature wants to have this anti-parallel for function. So what they do? They cannot have a system where the energies are fully symmetrized. That's something you're working on. They have to break a little of the symmetry of the energy to compensate for the entropy that favors the other one. So clearly, when nature selects its structures, it selects the one that's energetically favored to the AP, to the anti-parallel. That's the function one. But now I start to put mutations. But I'm putting mutations without selection. I'm not selecting for function, I'm just doing the mutations. So what happens? Random mutations shouldn't help the AP in principle. What happens? You start to favor the one that's kinetically easier. Right? So it's not as you, and then you start to observe faster and faster rates. But that means, doesn't mean you can fold out one. You still can populate both states. And if you populate a little of these states, you're going to bind RNA. You may not bind as strong, but you can fluctuate and bind. Okay? So that's why when you do in vitro, you observe it, but when you do in vivo, that you really need a lot of RNA to be bound, then the requirements are more stringent. You cannot just bind sporadically. You cannot just sit around and let the gel hang in there for a lifetime until you sporadically go and visit the less likely structure. Right? So that's where the situation is. And actually, not everybody agrees with this thing here, but we have some very, very cute experiments here. We have a friend, Dennis at Scripps, that is doing fret experiment into the system. It's a perfect system to do frets, because you can see which order you orient. So what he did, sort of very cool experiments, we don't have all the results yet, they're being done. So what they're doing here now is the following thing. And we have half of the experiments done, I can tell what half of the experiments are. Basically, he got this protein, wild type, and then he got the other one on the other side that we know it's AP, and then we got one in the middle, where you expect to have both. And what you observe, yes, from Fred data, this wild type is really anti, as expect. If you get the other one with the crystal structure is syn, you get syn. The parallel one, but this one in the middle, what she said was anti, he actually got syn, as we would expect. That's the most likely state. So that's the first half of the experiment. That already demonstrated. But since you want to demonstrate the full story, I told you what the experiment that being run right now. We're getting these things with the Fred experiments. You're getting that structure, but I'm telling you that every so often you fluctuate, right? So now you're dumping the RNA into the solution, and you expect that sometimes you're going to bind the RNA, and then you're going to trap into that anti-structure. You're going to start with everything syn, and if you wait long enough, you're going to start to build the anti-structure, right? That will be sort of the full end of the story that you've actually interconverted into these two structures. These experiments are not done yet, but these are sort of very cool experiments. And that's a case why I tell you, when you come for functional proteins, these things may be the case. Now I know, Daniel, I'm a little late, but I'm going to tell them just a short 5-minute story. Okay, Daniel? Just to tell them a little fun thing. Now, you come landscape, I gave you a little of a taste for function. But can you go to more functional, more wild system that we're talking about? So one of our favorite toys these days, the system to studies, is kinesin. Who knows what kinesin is? Kinesin is a taxi cab on a cell. Right? So if I just go forward, kinesin is very simple, right? Molecular motor that I've just shown you here. It has two big domains that are like the foots of it. Then it has this big neck here. And that's when you put some load in it, and this kinase is just keep moving. Okay? There are several very interesting stories. I'm going to just tell you in the interest of time half of this story, but I gave you the papers of the other half. But today I don't have time to discuss actually the most interesting step. That's the step forward. That's the one that you have here. But basically, the nice thing about this step, you can read on your own because I don't have time, but to show that basically how fast you move and how fast you relax is very important to guarantee neutrality. If you have just a problem with total equilibrium, you go in the wrong direction. But that takes a full lecture on its own, but it's the second paper. The first one is sort of a cool story, and I can tell you in 5 minutes, just so you have a feeling. So I'll tell you about this domain, and the only reason I want to tell you is how you can aggressively make structure-based models. That's actually work done by this guy, Shenbong Kyon, the postdoc group is going back to Korea now, but he's a very clever kid. So what you notice about this thing is, after you give this step, you have ATP bound here and you have ADP here. This thing is only bound here as long as you have ATP. Right, so the interesting question now is basically, you have to lose ADP, and then you have to have phosphorylation here. When you do that, you become ADP, and then you are ready to go. The danger here is the following thing. You look at this empty state here, so the protein can only bind to the microtube, and it can only bind ATP when it's fully structured. If it's distorted, it doesn't happen. Now the interesting thing here, you cannot bind ATP too early, because what happens is, if you bind ATP too early, you follow this stage, everything gets bound, phosphorylate, you go here, the microtube is gone. If you come to this other state here, and again you bind ATP, you go the same process. So you only can bind it later on in the process. You cannot have ATP on both heads. It's a very bad thing to happen, because then both get phosphorylated and you're in trouble. And you have association. So you want to make sure you keep this bound, empty state here. State is there bound, but empty until really all this process state, then you can take ATP, then you're ready to go for the cycle. If you don't do that, you fall into distress, and you do. That's what people call processivity. That means how many steps can you do that without making mistakes? Right? So these kinases are going so many steps, and when they make a mistake, they jump out. And if you do that too often, you lose processivity. Most of the systems have more than one kinase, so you can correct for the other one. But the question is, this is highly processive state, and they are moving in one direction, and you have to guarantee that. So how do you guarantee this process? That's an interesting situation that basically what I expect is, the idea of Shenbong is how can I keep this state disordered? All the way up to here. How can I keep this head disordered? All the way up to here. And then I can say, oh, now this head got ordered, now I can bind the ATP. So how did nature manage to do that? That was his idea. But can we do that with a very simplified model? And then I'm going to show the next 3 slides, because sort of a very cool idea. How can you do that? Just a couple of slides so that you can have a little feeling for it. So you see that's less than 1%. That means you have about 100, you go about 100 steps before you make a mistake. Okay, that's whatever. This is, then we said, okay, let's look all the crystal structure we have there. There is a crystal structure of the dimer of kinesin. That's how it looks like. He got the crystal structure. When I'm going to build a model like a Go model, I need to have structures, right? So he got this first structure. Just for you to get, the coil is this part here, where you're going to put the load afterwards, just to keep the names straight. And this is the neck linker. This is sort of, you have these big domains, and you have this stretch of things, the neck linker. That's where we're going to build stress into the molecular motor. Sometime in the region. That's a very important control entity into these things. And just if I continue, if I look at the crystal structure, these are 5 nanometers apart. Now, says there's a problem. How do things blow up? Things blow up because if you come, I'll just do a couple more. If you look in the nanotube, and the 2 binding sites on the nanotube, they're 8 nanometers apart. So you have a crystal structure that tells me this protein is very happy be 5 nanometers apart. But the nanotube, you have the 2 heads 8 nanometers apart. Okay? So you start to see that it's very hard to keep both bound and happy, right? And then he decided to build a model. Then when he built a model, he picked up a couple more structures. Right? There's a structure of a single domain bound to a piece of microtube. And then he got a structure of microtube, something else in microtube. He got all these structures. And then he built a structure model. But the model is built in the following way. All the contacts on this native structure are attractive. And all the contacts between the head and the microtube are attractive. The microtube is frozen, just for this exercise. So now what do you have? Right? So you're putting a system of interactions where the dimer is happy and the contacts with the microtube are happy. You see you have a problem, right? The dimer is starting to say 5 nanometers apart. If I want to satisfy all the interactions in the microtube, you have this 8 nanometers. So they're competing. Right? Or I keep the dimer happy, or I stretch the dimer to make the interaction with the microtube happy. So he built this competition. And the idea is maybe this competition structure is enough to do the control that I need. Okay, so you build a model just like the other one, a simple interaction, kilocalorie per interaction, typical interaction, all the most average way you can do, and you run this model. So what is very interesting is that when you run the simulation, this trailing head is much more structured than the leading head. I'll show you some data, but this tells you that because of the geometry of the microtube of the dimer, it's much easier to buy this one and the other one, the front one, it stays a little bit disordered. So we actually measure that. If you look at the thermal ensemble here, you can see that the leading head is really moving much more than this one. That's why these things are only blue, and you see these things are sort of moving along. Let's see if I can get another slide with a little bit of better numbers. These are just quantities that shows that this thing is that basically, I cannot read from here. Let's see from this side if I have a chance. Right, basically, this is the leading head, this is the trailing head, is much more ordered. The color part is ordered than the other one. So it means that you have a very highly stressed, that's what the Q tells you, larger Q tells you order. And just, since I'm out of time and I promised Daniel too fast, I just want to show you one thing here. These are comparisons to show that the leading head is much more disordered. But you can see these from our MSDs. If you come here, trailing heads about 2 angstrom, and this one's, and the, okay, things are much more disordered. But let's just go to what I really, or you see here, the trailing heads about 2 angstrom, the leading heads about 9.4 angstrom, our MSD. And the stuff here that I don't have time to show, most of the stuff is on the neck linker. But what's very cool is the following thing. Comes on this slide here. If I just do a very simple model for you, there's a worm-like model of this neck linker, and I assume I'm applying a force, and I'm going from 8 nanometer on the typical lens is 5 nanometers, okay? So you go from L is the total lens about the total lens about 5.7 nanometers at equilibrium. You add another 3.1 nanometers, that's the extension on the microtube. Then you have a persistence lens of about 0.5 nanometers, 5 angstrom for proteins, what's a good number to put in there, a worm-like model. If I put that, I get a force of the order about 12 to 15 piconewtons. Now we have a lot of single model guys here, and I'm just telling why this number is a very dangerous number. It's a great number, but that's the internal force into the system. Now the stalling force on the system has been measured by Bloch and other people. They are about 8 piconewtons. But it's very interesting to figure out how do I relate internal forces to stalling forces that apply to the load. You expect them to be related, but it's not. That's something you're working on it right now. It's very complicated, but it's just sort of rewarding to see that you're getting things on the right ballpark. What you expect, that this is the sort of enough strain force to keep the system from having the trailing head disordered until the last minute, when the other one comes out. So you cannot have the two heads ordered. If the trailing head is ordered, the leading head is disordered. And I'll go back to that. So what happens here is more interesting is that basically each residue increases tension by 2 piconewtons. And people notice, If you start to put more residues and make the net linker softer, you reduce processivity here. So a single residue here, we still work on the real number, but say basically the processivity is reduced by 2-fold when you insert when an amino acid insert, and 3 to 4-fold when you insert 12 or 6 additional. It makes it very flop. So you really need to have the neck linker under tension. That's kind of cool. And if you go back, I think the next slide is here. Let's just give the conclusions. These slides here, what you're seeing here, I don't have time to go to other steps, so I'm finishing here, is that basically the way you achieve that is that basically when you get here, this is bound. And as long as this is bound, this is disordered. So you can go over the entire cycle, and only when this ATP becomes ADP and gets out, that this one can get ordered. And when it's get ordered, then can bind the ATP. So so you really have to have that strain in there to do that. You don't want too much strain to make your life impossible to bind, but you want to have enough strain so the neck linker gets disordered, and a disordered neck linker you can see distort the ATP binding site sufficiently to go in there. Okay, so with that said, I'm going to stop here. I talked too much already this week. Have the chance to other people. But just to give a flavor of how we can come with models that simplified and try to bring to more interesting problems. Do we know all about it? No, we are going. Basically, we are going to complete different community. Just like the work Daniel was presenting. I was telling my wife, no, I said, we need too much protein folding. We have to move towards the sort of molecular motor community. We have to move towards the cell biology community. And her joke says, so you mean that now you want to have an entire new collection of enemies? I say, yeah, that's part of it. That's how it works. But thank you, guys.
You can take a few questions.
So I'm back there.
I have a question about the first energy plot you showed, where there was radius of duration versus Q. And you mentioned that you never see the minimum.
Yes, I'll show you.